Hi there, this is Heath. We're on the second of two lectures for determinants from week 6. Let's go ahead and get started. In the last video, we saw that square matrices have determinants, but non-square matrices do not. We saw how to find the determinant of a matrix using cofactor expansion. We saw that we can find the determinant of a matrix in echelon form by multiplying the entries going down the main diagonal, and that we can row reduce to help find a determinant, but row reduction changes the determinant so that we have to keep track of these changes. In this video, we'll learn a technique for combining row reduction with cofactor expansion so that we can find the determinant of even large matrices without doing too much effort. This is example 116. We would like to compute the determinant of this large 5 by 5 matrix. There are some zeros, but I don't see a good way of doing this just using cofactor expansion. So we're going to try to row reduce this matrix. And the first number we're going to want to do is change the 1/2 to a 1. Before we do that, we're going to set the determinant equal to some variable. We'll call that variable x. And then we have something here that stores the value of the determinant. And now when we do the row reduction step that changes the 1/2 to a 1, we're replacing row 1 with 2 times row 1, but that causes the determinant to double, and so we also double the x on the other side. Anytime we perform a row reduction step that changes the value of the determinant, we record the change on this side. These are changes due to row reduction. So what's the next step we're going to do? We're going to try to get rid of this 1 right here. We can do that by taking row 3 minus row 1, making that the new row 3. But this step doesn't change the determinant, and so we still have 2x on the right-hand side. Now this first column corresponds with what we would like an echelon form to look like. The matrix is an echelon form, but the first column has the correct form. And so we're going to eliminate the first column and the first row of the matrix. We'll actually eliminate the first column and the first row from this matrix. But we don't want to lose this 1. The 1 comes out to the front. 1 doesn't change anything, but I want to show you what happens. The rest of the numbers get discarded. The only number that's important here is that 1. And so we have a 1 out front, and now the determinant is a smaller matrix, and we still have a 2x on the right-hand side. So let's keep going. The next step we would like to do is bring this 3 up here, because the leading entry in this row should be to the left of the leading entry in the second row. And so we're going to switch the 2 rows. But switching 2 rows causes a sign change, and that sign change we record on the right side. Again, anything that happens because of row reduction, we record on the right side. But the first column here is once again in echelon form. And so we will eliminate the first column and the first row, but we will salvage the 3 where they intersect, and that number comes out to the front. And so now we have 3 times the determinant of an even smaller matrix equals to negative 2x. So what's the next step we would like to do? We'd like to get rid of this 3. And we can do that by multiplying this row by 2 and this row by 3 and subtracting. The common multiple of 3 and 2 is 6, so we'll scale this up to a 6, scale this up to a 6, we subtract. That's the step. 2 times row 3 minus 3 times row 1 becomes a new row 3. But because we're changing row 3, the determinant doubles. And so instead of having a negative 2x on this side, we now have a negative 4x. And then once again, this column is in echelon form. So we eliminate the column and the row, but we salvage the 2 by bringing it up to a front. And now the 2 and the 3 will combine to give me a 6. And now I have 6 times the determinant of a 2 by 2 matrix equals the negative 4x. But at this stage, we can eliminate the determinant of the 2 by 2 matrix because we can actually multiply this out. 3 times negative 13 is negative 39. 4 times 3 is 12. Negative 39 minus 12 is negative 51. And so we get 6 times negative 51 equals negative 4x. And then we solve for x. X equals 76.5. That's the determinant of the original matrix before we made any changes at all to it. We have the determinant of the original matrix because we recorded all of the values we took out because of cofactors and all of the changes we made due to row reduction. Let's try one more example. We're going to try to compute the determinant of this matrix right here. Okay? So in order to put this into echelon form, I need to change this entry and I need to change this entry. And I'm going to start by setting this determinant equal to some variable x. So the determinant of this matrix is equal to x. I can cancel the negative 4 by adding positive 4. That's going to be row 1 plus row 3. So 4 and negative 4 is 0. 0 and 2 is still 2. 3 and 5 is 8. 1 and 7 is also 8. But to get rid of this 2, I'm going to have to scale this 2 up to a 4. 2 times row 4 minus row 1. And so what do we get? 4 minus 4 is 0. 0 minus 0 is 0. 2 minus 3 is negative 1. And 0 minus 1 is also negative 1. What happened to the determinant when we did this? This step does not change the determinant, but this step causes the determinant to go up by a factor of 2. And so we have this matrix and its determinant is equal to 2x. This matrix is now in echelon form. Well, not the whole matrix, just the first column, sorry. So I'm going to eliminate the first column and the first row, but I have to preserve the 4 that was in that position. So now I have 4 times 2, 4, negative 2, 2, 8, 8, 0, negative 1, negative 1, equals to 2x. And I'm still taking the determinant of this. I left off the word determinant, sorry. I would like to get rid of this 2, and so I'm going to need to make row 2 minus row 1. And so 2 minus 2 is 0. 8 minus 4 is 4. 8 minus negative 2 is positive 10. We still have a 4 in front of all of this. And a 2x on this side. This step did not change the determinant, so we still have a 2x. But once again, we have a column that's in echelon form. We can eliminate the column and the row, but the 2 has to come out in front. And so now we have 8 times the determinant of 4, 10, negative 1, negative 1 equals to 2x. Now that we're down to a 2 by 2 determinant, though, we can solve this. This is negative 4 minus a negative 10. Negative 4 minus negative 10 is negative 4 plus 10, which is 6. 8 times 6 is equal to 2x. 48 equals to 2x. And so x is equal to 24. The determinant of this matrix is 24.